Picture a log, 40 feet long, 5 feet in diameter, weighing 40 tons, suspended 200 feet in the air, swinging through the forest on a steel cable, accelerating toward a landing area at 30 miles per hour, clearing ravines and stumps and obstacles that would stop any ground-based operation. Not being dragged, flying. This was high-lead logging, the innovation that dominated the Pacific Northwest timber industry from the 1910s through the 1960s, that made it possible to harvest timber from terrain so steep and so broken that no other method could touch it. The system used a living tree, topped and rigged, as a tower. A steam-powered yarder weighing 40 tons with drums wrapped with cable as the engine. And physics, geometry, and mechanical advantage and sheer brute force as the tool. It was elegant, it was effective, and it was spectacularly dangerous. Cables under 50 tons of tension snapped and cut men in half. Spar trees, supporting loads they were never designed for, failed and collapsed, crushing crews. And the climbers, the men who scaled 200-foot trees to top them and rig them, worked a job with a fatality rate that made logging, already the deadliest occupation in America, even deadlier. This is the story of high-lead logging, how it worked, why it was necessary, and what it cost. Let's start with the problem, because high-lead logging was a solution to a specific, urgent challenge. By the early 1900s, the accessible timber in the Pacific Northwest was being cut rapidly. The flat valleys, the gentle slopes, the areas where logs could be dragged to rivers or railroads by ground skidding, were being harvested. What remained was timber in terrain that was difficult or impossible to reach with conventional methods. Steep slopes, grades of 50, 60, 70% or more. Ravines and gullies that cut through the landscape. Rocky outcrops and uneven ground. This terrain held enormous volumes of Douglas fir, Sitka spruce, western red cedar, valuable timber that the companies wanted but couldn't extract efficiently. Ground skidding, the standard method of the era, had clear limitations. A steam donkey, positioned at a central point, would drag logs from the cutting sites to the landing using a cable. The cable was attached to the log with a choker, and the donkey would wind in the cable, pulling the log across the ground. This worked on flat or gently sloping terrain, but on steep slopes, the logs would dig in, creating trenches, or they'd hang up on stumps and rocks, requiring the crew to stop, free the log, and restart. The process was slow, destructive to the forest floor, and limited in the terrain it could handle. Logs in ravines, on the far side of creeks, on slopes too steep for the cable to pull effectively, were often abandoned. The economic waste was significant, and the companies needed a better method. The innovation that became high-lead logging emerged in the Pacific Northwest in the early 1900s, with multiple claimants to the invention. Some sources credit riggers in the Grays Harbor area of Washington. Others point to operations in Oregon. What's clear is that the core insight, using a tall tree as a tower to lift logs clear of the ground, appeared in several places nearly simultaneously, suggesting it was an idea whose time had come. The physics were straightforward. If you position a block, a pulley, at the top of a tall tree, and run your cable through it, the cable creates an angle. The vertical component of that angle lifts the log, and the horizontal component pulls it toward the donkey. The higher the block, the greater the lift. A block 200 feet high could lift a log 50, 70, 100 feet off the ground, clearing all obstacles, turning rough terrain into open air. The log wouldn't drag. It would fly, suspended, swinging through the forest like a pendulum, landing at the yarder clear of everything it would have hung up on with ground skidding. The first systems were crude, experimental, but the results were immediate. Logs from impossible terrain were reaching the landings. The companies saw the potential, invested in the equipment and the training, and by the 1920s, high-lead logging was the dominant method in steep country operations. The spar tree was the foundation of the system, and selecting, preparing, and rigging a spar was a major operation requiring specialized skill and significant risk. A spar tree had to meet exacting criteria. Height was the first requirement. The taller the spar, the greater the lift, and the longer the reach. Spar trees in high-lead operations ranged from 150 feet to over 250 feet. The tree also had to be straight, with minimal taper, so that the top, where the rigging would be installed, was still thick enough to support the loads. Diameter at the base needed to be 4 feet minimum, and 6 or more feet was preferred for the largest operations. And the tree had to be healthy, solid wood with no significant rot or defects, because the forces it would endure were extreme. Douglas fir was the preferred species in the Pacific Northwest because it grew tall, straight, and strong. Sitka spruce was used in coastal areas, redwood in California. The rigging engineer, an experienced man who understood the physics and the risks, would survey the setting and select the spar. Once selected, the tree was prepared. All the branches had to be removed, a process called limbing. This was done by the climber, starting from the ground and working up, using an axe to chop off each branch flush with the trunk. Limbing a 200-foot tree could take a full day. Once limbed, the spar was a bare pole, smooth and clean. Next, the guy lines were installed. Guy lines were cables anchored to stumps or other trees in multiple directions around the spar, tensioned to hold the spar upright against the pole of the main line. The guy lines were critical. Without them, the spar would be pulled over by the load. With them, the spar could withstand tensions of 20, 30, 40 tons or more. The physics involved were brutal. The spar tree, once rigged, would bear the weight of the suspended log plus the tension in the cable. A 40-ton log suspended on a cable creates a load on the spar that can exceed 60 tons when accounting for the angles and the dynamic forces of the log swinging. The spar had to support this in compression without buckling, and it had to resist the lateral forces of the swinging log without snapping. The safety factor was minimal. The trees were selected to be just strong enough, with little margin for error, because finding a tree that was significantly overbuilt was impossible. Most available trees were at their limits. The rigging at the top of the spar, the blocks and cables, had to be installed, and that required a climber. The climber was a specialist, a man who did one job and did it in conditions that were as dangerous as any in the logging industry. Climbers were typically young, in their 20s or 30s, because the job required agility, strength, and a certain disregard for mortality. The pay was premium, $8 to $15 a day, when laborers made $3 to $5, because the skill was rare and the risk was extraordinary. Climbers were celebrities in the camps, respected and feared, known by name, watched with a mix of admiration and dread. The equipment was minimal. Climbing spurs, steel spikes about 3 inches long, strapped to the climber's boots. A climbing rope or belt. A loop of manila rope or wire rope that went around the tree and around the climber's waist or chest. And tools, a saw, an axe, additional ropes for rigging, all carried on the climber's belt. There was no safety backup, no redundant line, no harness in the modern sense. The rope around the tree was the only thing between the climber and a 200-foot fall. The technique was simple in concept, exhausting in execution. The climber would position himself facing the tree, stab the spurs into the bark, flip the rope up the trunk a foot or two, lean back against the rope, and step up, driving the spurs deeper. Repeat. Stab, flip, step. Stab, flip, step. A rhythm that had to be maintained for the entire climb. A large spar, 200 feet tall, could take 30 minutes to an hour to climb, depending on the climber's skill and stamina. At height, the tree swayed in the wind, sometimes several feet in each direction, and the climber swayed with it, holding on, waiting for the movement to settle before continuing. The psychological challenge was immense. You couldn't look down. If you did, if you thought about the height, the fear would paralyze you. You focused on the tree, on the next step, on the rhythm, and you ignored the void below. Topping the tree was the climax of the climb and the most dangerous moment. The climber would ascend to the height where the top was to be removed, typically a point where the trunk was still 12 to 24 inches in diameter, thick enough to support the rigging, but thin enough that the remaining spar would flex without breaking. The climber would chop a notch, an undercut, on the side of the tree, facing the direction he wanted the top to fall. Then he'd saw from the opposite side, the back cut, cutting through the trunk while standing on his spurs, leaning against his rope, working the saw with both hands. The treetop, 50, 70, 100 feet of tree above the cut, would begin to lean, then fall, crashing down through the surrounding canopy. And the moment the top separated, the spar would whip. The sudden loss of the top's weight, the release of the tension that had been holding the top in place, caused the entire spar to oscillate violently. The climber, still attached by his rope and spurs, would be whipped back and forth, sometimes through arcs of 10 or 15 feet, his body flung like a rag doll. The only option was to hold on, to keep the spurs dug in, to ride the whip until the oscillations dampened. Some climbers were thrown clear, their spurs ripped out of the bark, their ropes snapping or slipping. They fell, 200 feet, and died on impact. Some were struck by the falling top, if the top didn't fall clear, if it hung up in the canopy or fell back toward the spar. And some discovered, in the moment the top fell, that the spar had a rotten core, that the trunk was hollow or weakened, and the spar broke, snapping at the cut or below, and the climber rode the collapsing spar to the ground. The death rate for climbers was staggering. Estimates based on camp records and oral histories suggest that 10 to 20% of men who worked as climbers full-time died on the job. Not over a lifetime, over a career that might last 5 or 10 years. It was one of the few jobs in logging where death was more likely than survival if you did it long enough. Once the spar was topped and the climber descended, the rigging crew took over. Installing the blocks and cables at the top of the spar, 200 feet up, required hauling heavy equipment up the spar using a system of lighter lines. A climber would carry a light rope, maybe a half-inch line, to the top and drop it down. That line would be used to pull up a heavier line, and that heavier line would pull up the block, a steel pulley weighing several hundred pounds, and the cables. The main line, the cable that would pull the logs, ran from the yarder up to the block at the top of the spar and out into the woods. The main line was typically 3/4 of an inch to 1.5 inches in diameter, made of steel wire rope, capable of handling tensions of 20 to 50 tons. The haulback line, a secondary cable, ran parallel to the main line and was used to return the chokers to the woods after a log was delivered. The system was elegant. Pull a log in on the main line, send the choker back out on the haulback, repeat. The blocks at the top of the spar redirected the cables, changing the direction of pull from horizontal to angled, creating the lift. The guy lines, tensioned and anchored, held the spar against the pull. The entire system was under constant, immense stress, and every component was a potential failure point. The physics of lift are straightforward, but the numbers are staggering. A cable running from a yarder to a block 200 feet up and then out to a log 1,000 feet away creates an angle. That angle determines how much of the cable's pull goes into lifting the log versus dragging it. With a high spar and a long reach, the angle is shallow and the lift is significant. A typical high-lead system could lift a log 50 to 100 feet off the ground at the midpoint of the pull, clearing stumps, rocks, ravines, everything. The log would rise as it was pulled in, swinging in a pendulum arc, accelerating toward the spar, then slowing as it approached the landing. The physics were beautiful. The results, logs flying through the air, clearing terrain that had been impassable, were spectacular. The operation of a high-lead system was a coordinated effort involving a crew of 6 to 12 men, each with a specific role, working in an environment where mistakes were lethal. The choker setters worked in the woods, attaching the cables to the logs. This was skilled and dangerous work. The log, once felled and bucked, was lying on the ground, often on a slope, potentially unstable. The choker setter had to position the choker, a loop of cable, around the log, typically near one end, and attach it to the main line using a bell and shackle. Then he had to clear the area, because when the yarder pulled, the log would move and anything in its path would be crushed. The choker setter's position under the future flight path of the log was inherently dangerous. If the choker slipped, if the log rolled, if the cable broke, the setter could be killed instantly. The signal system communicated between the crew in the woods and the yarder engineer, who couldn't see the logs or the crew. In the early days, this was done with a whistle punk, a worker who operated a steam whistle on the yarder using a wire that ran out to the woods. Later, it was done with radio or horn signals. 1 whistle meant stop, 2 meant go ahead slow, 3 meant go ahead fast. A continuous whistle meant emergency. The yarder engineer controlled the steam donkey, engaging the drum, managing the speed, and stopping when signaled. He worked by sound and feel, interpreting the tension in the cable, listening for the whistle signals, trusting that the crew in the woods knew what they were doing. When the signal came to pull, the engineer engaged the drum. The cable tightened, the tension built, and the log began to move. The rear end of the log, where the choker was attached, would lift first, rising off the ground. The front end would follow, dragging briefly, then lifting as the angle increased. The log would accelerate, swinging toward the spar, clearing the ground, flying. The speed was significant, 20 to 30 miles per hour in the final approach, and the momentum was enormous. At the landing, the log was lowered, the choker removed, and the haulback line pulled the empty choker back out to the woods for the next log. The cycle time, from attaching the choker to delivering the log, ranged from 5 to 15 minutes, depending on the distance and the terrain. A good crew could move 50 to 100 logs per day, far more than ground skidding could achieve in the same terrain. The productivity gains were the reason high-lead logging was adopted so rapidly. It could work on slopes up to 80 or 90% grade, slopes where ground skidding was impossible. It could span ravines and creeks without building roads or bridges, and it could reach logs up to a mile from the yarder, far beyond the range of ground systems. But the productivity came at a cost. High-lead logging was significantly more dangerous than ground skidding, and the dangers were new, specific to the system. Cable failures were the most common killer. The cables were under immense tension, 20 to 50 tons, and they were subject to wear, kinking, and hidden damage. A cable that looked sound could have internal broken wires, stress fractures that weren't visible. When a cable under tension failed, it snapped, and the stored energy was released instantaneously. The cable whipped, moving faster than the eye could see, cutting through anything in its path. Men were decapitated, cut in half, killed before they could react. In 1923, in an operation near Coos Bay, Oregon, a mainline cable snapped under load. The cable whipped back toward the yarder, traveled over 300 yards, and tore through a bunkhouse where off-shift workers were sleeping. 3 men were killed, their bodies found with massive lacerations from the cable. The company's response was to note the incident, replace the cable, and resume operations. Spar failures were less common, but more catastrophic. A spar tree, supporting loads at the edge of its capacity, could fail in several ways. If the core was rotten, a condition not always detectable from the outside, the spar could snap under load, breaking at the weak point. If a guy line failed, the spar could fall, no longer held upright against the pull. If the spar was overloaded, pulling a log that was too heavy or at a bad angle, the spar could buckle, the wood crushing under compression. When a spar failed, it collapsed and anything below it was crushed. In 1931, in Washington state, a spar tree collapsed during a pull. The spar broke at a rotten section about 100 feet up, and the top portion, 150 feet of tree, fell. 5 men were killed, including the climber, who was on the spar at the time, rigging a new block. The spar's collapse destroyed the yarder, crushed the rigging, and shut down the operation for weeks. Flying logs were another hazard. If a choker slipped, if the attachment failed, the log would fall from whatever height it had been lifted. A 40-ton log falling from 100 feet would hit the ground with enough force to bury itself, and anyone below would be obliterated. The swing of the logs, the pendulum motion as they were pulled in, also created danger. A log swinging through the forest at 30 miles per hour could hit a standing tree and ricochet, changing direction unpredictably. The rigging crew, working on the ground, had to stay clear of the swing path, but in dense forest, predicting exactly where a log would go was impossible. The death rates in high-lead logging were significantly higher than in ground skidding operations. Logging was already the deadliest occupation in America, with fatality rates several times higher than mining or construction. High-lead logging, by introducing new mechanisms of death, cables under extreme tension, spar trees under extreme loads, logs flying through the air, made the job even deadlier. Estimates suggest that high-lead operations had fatality rates 2 to 3 times higher than ground skidding, and the climbers, the men who topped the spars, had fatality rates approaching 20% over a career. The companies accepted this. The productivity gains justified the risk in their calculation. Men were replaceable. The timber had to come out. And the alternative, leaving timber in steep terrain, was economically unacceptable. The evolution of high-lead logging continued through the mid-20th century. The next major innovation was the skyline system, a further evolution that increased capacity and reach. A skyline used 2 spar trees, or anchor points, with a cable strung between them at height. Logs were attached to a carriage that traveled on the skyline cable, fully suspended, like a gondola. The skyline system could span longer distances, could work even steeper terrain, and could lift logs higher. But it was more complex, more expensive, and introduced new dangers. The cables were under even greater tension, the rigging was more elaborate, and the potential for catastrophic failure was higher. By the 1940s and 50s, steel towers began to replace tree spars. Portable steel towers, built in sections and assembled on site, offered advantages. They were reusable, could be moved from setting to setting, and had predictable strength characteristics. They also eliminated the need for climbers because there was no tree to top. The steel tower era marked the end of the climber's role, and with it, the end of one of the most dangerous and skilled jobs in logging history. The final decline of cable logging came with the post-World War II expansion of road building and trucking. Building roads into steep terrain became economically feasible with improved equipment, bulldozers, and graders. Trucks offered flexibility and speed that cable systems couldn't match. By the 1960s, cable logging was being relegated to the steepest, most inaccessible terrain, and even there it was often replaced by helicopters, which could lift logs from areas that even cables couldn't reach. What remains today of the high-lead era is scattered and fading. In the forests of the Pacific Northwest, you can still find spar tree stumps, topped flat 100 years ago, standing as monuments to the system. The stumps are massive, 6, 8, 10 feet in diameter, cut cleanly at a height of 150 or 200 feet, the top gone, the trunk scarred by guy-line cables and climbing spurs. Some stumps have trees growing on top of them, second-growth Douglas fir sprouting from the rot at the center of the old spar. Photographs from the era, black and white images, show the system in operation. Logs suspended in midair, swinging on cables, crews working below, spar trees standing bare and tall against the sky. The images are dramatic, almost unbelievable. Logs that weigh tons floating through the forest. There are museums with artifacts, blocks and cables and climbing spurs, and oral histories from the men who worked the systems, recorded before they died. The stories are consistent. The work was brutal, the danger was constant, and the skill required was immense. Modern cable logging still exists, used in specific applications where terrain is too steep for ground-based equipment and too expensive for helicopter logging. But the systems are mechanized, computer-controlled, with steel towers and hydraulic yarders. The climbers are gone. The skill of topping a 200-foot tree while standing on spurs is lost, known only through the photographs and the stories. High-lead logging dominated the Pacific Northwest timber industry for 50 years, from the 1910s through the 1960s. It made it possible to harvest timber from terrain that had been inaccessible, turning steep slopes and broken ground into productive logging settings. It increased productivity, reduced waste, and generated enormous profits for the companies. And it killed hundreds of men in ways that were predictable and preventable, but accepted as the cost of doing business. So here's to the climbers, the men who scaled 200-foot trees with nothing but spurs and a rope, who topped those trees while the wind swayed them and the spar whipped beneath them, who rigged the blocks and installed the cables that made the system work. Here's to the choker setters who worked under flying logs, who positioned themselves in the danger zone every day, who set the rigging and cleared out and hoped the cable held. Here's to the yarder engineers who controlled machines they couldn't see, who worked by feel and sound, who managed forces that could kill with a moment's inattention. Here's to the rigging crews who built the systems, who tensioned the guy lines, who maintained the cables, who kept the operation running despite the constant breakdowns and the constant danger. And here's to the ones who didn't make it, the climbers who fell, the choker setters who were crushed, the men who were cut in half by snapping cables, the crews who were buried under collapsing spars. They moved the timber. They conquered the terrain. They proved that physics and engineering and human labor could overcome obstacles that seemed insurmountable. They did it for wages that were good but not great, in conditions that were dangerous beyond modern comprehension. And the logs flew through the air, 40 tons of wood swinging on cables, clearing ravines and stumps, landing at the yarders, feeding the mills, building the cities. The high-lead era is over. The climbers are gone. The spar trees stand as stumps, mute witnesses to a time when men flew logs through the forest and died doing it. The innovation was real. The achievement was real. And the cost, measured in lives, was real. The forests remember, even if we've forgotten.